Good afternoon, everyone. Thank you for being here. Today, I'm excited to present our work on swept volume computation with enhanced geometric detail preservation. This is joint work with my colleagues from Shandong University, Qingdao University of Science and Technology, and Texas A&M University. Let me start with a question that motivates our work. Will they collide? Imagine a robot vacuum navigating through your home. It needs to move around furniture, avoid walls, and reach every corner safely. Or consider an autonomous vehicle trying to park in a tight underground garage. One wrong move could result in a collision. So here's the critical question. How do we know if the robot or car will hit obstacles during motion? The answer is, we need to compute the space occupied during motion. And that space, the union of all positions an object occupies as it moves, is what we call a swept volume. So what exactly is a swept volume? Let's define it properly. A swept volume is formally defined as the union of all spatial positions occupied by an object as it moves along a trajectory. Here's a visual example. You can see a small object, this green shape, following a curved blue trajectory. The resulting swept volume is this beautiful torus-like structure in yellow. It's the continuous region traced out by the object during its entire motion. Mathematically, we express it as the union of m, t, for all time t in the interval 0, t, where m, t, represents the object's position at time t. Now that we understand what swept volumes are, let's see why they matter in practice. Swept volumes are fundamental to many real-world applications. In manufacturing, we need to verify that tool paths won't collide with the workpiece or fixtures. In robotics, swept volumes enable safe path planning and collision avoidance for robot manipulators. For autonomous driving, computing swept volumes is essential for safe navigation, especially in complex environments like parking garages or tight urban streets. And in virtual reality, swept volumes help us create realistic dynamic scene interactions. This means accurate swept volumes equal safe and efficient motion. However, computing these swept volumes accurately is far from trivial. Computing swept volumes is actually quite challenging. Why? First, we're dealing with complex geometries, objects with irregular shapes and intricate features. Second, the motion itself is often intricate, curved trajectories combined with rotations, not just simple straight-line movements. Third, objects may exhibit self-intersections, where the trajectory crosses itself, creating complex overlapping regions. And finally, we need detail preservation. Sharp geometric features must remain sharp in the final result. Given these challenges, researchers have explored different strategies over the years. The first family of methods are explicit geometry-based approaches. The core idea is to directly track and construct swept volume boundaries from mesh surfaces. These methods trace how vertices and edges move, then attempt to construct the outer surface explicitly. However, they face fundamental challenges. First, robustness issues. When surfaces interact in complex ways during motion, these methods struggle to handle all the geometric cases correctly. Second, limited motion types. They typically only work well for restricted scenarios. And third, expensive computation. They require complex Boolean operations and intersection tests, which become prohibitively slow for intricate motions. Implicit methods use distance fields instead of explicit meshes. The stamping approach samples the object at discrete time steps, computes a sign distance field at each sample, combines them by taking the minimum value, and extracts the final surface. More recent 4D spacetime methods formulate the problem as an optimization, computing distance values throughout spacetime using numerical continuation. But these approaches also have significant limitations. Stamping produces zigzag artifacts due to discrete temporal sampling. You can see these stair-step patterns in the zoomed view. The optimization in 4D methods is slow, and can get stuck in local minima. Most critically, both use a single distance field per spatial element, which means they lose geometric details at trajectory intersections. Our key insight comes from a simple observation. Motion is relative. We can analyze the same motion from any reference frame. Traditionally, we fix our coordinate system in space and track how the object moves through it. But we can invert this perspective. Instead of tracking a moving object, we can fix the object in place and ask, how do spatial points move relative to it? Here's the crucial insight. A point is inside the swept volume if and only if its inverse trajectory intersects the static object. This gives us an exact equivalence. We've transformed the problem of tracking a complex moving object into the simpler problem of analyzing individual point trajectories. This perspective shift is the foundation of our entire approach. To actually compute distances, we start with the original problem, an object M moving along some trajectory from time t0 to t1. We want to know if a query point Q is inside the swept volume. Using our key observation, we invert the motion perspective. Now the object M stays fixed, and the query point Q traces an inverse trajectory, going backwards through the motion. Here's a crucial simplification. For sufficiently short time intervals, this curved inverse trajectory can be well approximated as a straight line segment. This is important because computing distances to line segments is much simpler than dealing with arbitrary curves. With this linear approximation, we can efficiently compute the distance. The distance from point Q to the swept volume becomes approximately the distance from this line segment to the static object M. So we've reduced the swept volume distance computation to a simple geometric query, line-to-model distance. And we can compute this efficiently for every point in space, giving us a complete distance field. But there's still a challenge. The challenge is, how do we preserve fine geometric details? When an object follows a complex trajectory, different time segments may create intersecting or overlapping features. Traditional methods use a single distance field per spatial element. But a single field cannot represent multiple surface sheets passing through the same region. As you can see in this close-up, details are lost and the surface becomes blurred. Our solution uses multiple distance fields. The same region, computed with our method, preserves all the fine features clearly. Here's how it works. We partition the motion into time segments. Each segment generates its own swept volume, and each swept volume contributes a distance field. A single tetrahedral element stores multiple fields, one for each relevant time segment. The key insight: multiple fields capture intersecting features that single fields miss. With multiple fields in hand, the question becomes, how do we turn these into a single, coherent surface? This is where our 4D incremental cutting comes in. Let me explain with a 2D example first. The top shows a triangle mesh with the swept volume. Below, you see how we extract the surface from a single triangle. We lift the triangle into 3D by adding a distance dimension, cut it with multiple planes representing different fields, compute the lower envelope, and intersect with the zero level to get the final contour. For 3D surface extraction, the idea is the same with 5 key steps. Spatial discretization: partition space into tetrahedra. Multiple fields: each tetrahedron stores multiple distance fields, one per time segment. Height equals distance. We add a fourth dimension W to represent distance values. Incremental cutting: cut a 4D prism with hyperplanes from each field, keeping the lower envelope. Extract I's equals 0. Intersect the envelope with W equals 0 to get the swept volume surface. The key advantage is that each tetrahedron is independent, making this perfectly parallelizable. Now let's see the full pipeline. Here's our complete method. We start with spatio-temporal discretization, partitioning both space into tetrahedra and time into segments. Then comes distance field propagation. For each time segment, we compute and propagate distance fields through the tetrahedral mesh using our inverse motion approach. Next, swept volume extraction using 4D incremental cutting, processing each tetrahedron independently to extract surface patches. And finally, we get the result, a clean, detailed swept volume that preserves all geometric features. Here are visual comparisons across different models and motion types. The stamping method, row 2, produces noticeable zigzag artifacts. Look at this close-up on the cup handle. You can see the stair-step pattern from discrete time sampling. The recent 4D spacetime method performs better, but still loses some fine details. In these zoomed regions, you can see the surfaces are somewhat smoothed out. Our method, bottom row, preserves sharp features clearly. Our method preserves sharp features without artifacts. For quantitative validation, we used a case with a known analytical solution, a sphere moving along a circular trajectory. We measured 3 metrics against the ground truth. The results show our method outperforms both baselines: lower chamfer distance, lower Hausdorff distance, and faster computation time. Here's a gallery showing the diversity of shapes and motions our method can handle. Complex topologies, intricate trajectories, translation, rotation, screw motions, and various combinations. From simple shapes following complex paths to complex shapes with varied motions, our method handles them all robustly. Our method has 2 key parameters, temporal and spatial resolution. These results show performance under different parameter settings. For temporal resolution, more time steps give better quality but increase computation time. For spatial resolution, finer grids produce smoother surfaces but are more expensive. There's a clear quality-efficiency trade-off. We have 3 main limitations. First, uniform temporal discretization. We use equal time steps everywhere. Second, uniform spatial tessellation. The same resolution is applied throughout the entire space. Third, we only support rigid transformations. No scaling or deformation yet. These uniform strategies lead to wasted computational resources. For future work, we're exploring adaptive discretization in both time and space to improve efficiency, and extending the framework to handle deformable objects. So, to summarize, we've presented a novel approach to swept volume computation. We introduced 3 key technical contributions. Motion inversion. By fixing the object and tracing inverse point trajectories, we simplified complex trajectory analysis. Multiple distance fields. By storing multiple fields per element, we preserved fine geometric details that traditional single-field methods lose. 4D incremental cutting. By computing the lower envelope in 4D space, we achieved robust surface extraction from multiple fields. These contributions translate into concrete benefits: higher accuracy with lower chamfer and Hausdorff distances, faster computation, and better detail preservation with no artifacts and sharp features maintained. By rethinking the problem through motion perspective inversion and using multi-field representation with 4D cutting, we've advanced the state-of-the-art in swept volume computation. Thank you for your attention. I'm happy to take your questions.